Okay, everyone, let's go ahead and... All right, everyone, let's go ahead and get started. So today we are going to finish up Domain 1 and try to get through Domain 2. So we're going to start off with Domain 1.4 of our SecurityX exam. One last thing I'm going to talk to you guys about. At the end of the course today, we're going to do a Linux lab together. I'm just going to show it on the screen. I'll upload the recording to the Google Drive in the afternoon. The SecurityX exam, around like one of the very first like 10 to 15 questions, I can't remember, it's been a long time since I've taken it, has a Linux question. And essentially it actually puts you into a Linux virtual machine environment, and then you have to find out how to stop a malicious data exfiltration. So I'm going to walk you through those steps at the end of class today. So when I'm done teaching the slides, we'll take a 2-minute break. We'll come back and I'll have a VM pulled up and I'll walk you through the steps and give you the exact commands you'll need, okay? Alrighty. So, domain 1.4.1, given a scenario, perform threat modeling activities, attack characteristics, and attack patterns. So you can see this is the exam objectives for domain 1.4, and in red is what we're going to go over in this section. So the first thing we're going to talk about is just threat actors in general. You know, what does that term mean and what are we talking about? So the common term we hear is hacker, but in enterprise, blue team, cybersecurity, defense, threat actor is more accurate, and what we're trying to describe is who and what and why would someone try to attack our network, try to exploit us, try to do social engineering against us. There's going to be a lot of different motivations, a lot of different sophistication levels, and a lot of different capabilities and resources amongst different threat actors. There could be threat actor teams, it could be individual, they could be nation state sponsored, they could be a hacktivist, they could be corporate espionage. And once we start to understand the different threat actors that could be targeting our sector, our industry, or our business, it can help us with our defense of it. It's kind of like learning the TTPs of different threat actors that have commonly attacked maybe your industry during your threat hunting activities, can help in your threat modeling to better deter, detect, remediate, and prevent attackers from getting into your network. So at the core of threat modeling is a threat actor. A threat actor is any individual, group, or organization capable of intentionally harming a system, network, or organization. And again, they're not all created equal. Okay, so different motivations could be financial. So motivation explains why a threat actor targets a system. And what we're saying here is if someone just has the capability to hack, to attack, to cause harm on your environment, well, this is the why behind it. What is their motivation? So financial motivation. Financially motivated attackers seek monetary gain. This is the most common form of cyber attack motivation. These attackers often target organizations that store valuable data such as payment card information, customer records, or financial credentials. A great example in the real world, right? It's June 2nd, this happened about a week ago, was Canvas. This was essentially a financial hack, right? And why? Because, this is just a learning management system that all colleges, universities use nowadays. Well, because it was ransomware, right? It was a ransomware attack, and they tried to hide that they didn't pay the ransom, but they did. So the motivation was financial, is we shut down your services, we got a hold of all this confidential student data, and now you have to pay our ransom, right? See, even the AI was so funny. Yes, it didn't get hacked. So we can just type in ransomware attack. There, that's better. But yeah, it was a ransomware attack, and then they actually ended up paying the ransom. So it does happen. It does happen still in the big 2026. It's still happening, these kind of hacks or attacks. Okay, other motivations, geopolitical, hacktivism, or notoriety. So geopolitical is probably the one that we're going to be most familiar with, the different red teams amongst our adversaries, our near peers. But, America also has their red teams sitting up at the NSA as well that conduct red team activities globally. Other countries do it, right? It's almost like one of the domains of fighting now, right, is cybersecurity, cyber attacks. So geopolitically motivated attackers are associated with what we call nation states. So that's what we're going to call it in the CompTIA SecurityX exam. Nation state actors have geopolitical reasons and they're acting on behalf of their government. As we know, some countries like to obfuscate that as well, like Russia's red teams are not technically Russian government backed, right? They give themselves names, or we name them, like the Sandworm teams, a very famous Russian backed advanced persistent threat team or threat actor that is not sponsored by the Russian government, quote unquote, but they are, right? And what are we talking about with geopolitical threat actors? What do we need to know about for the SecurityX exam? Is that they're highly sophisticated and they're well funded. They have a lot of resources. And a lot of times these threat actors can live in your environments going undetected because they're skilled, they're highly skilled, and they're highly trained, okay? So a hacktivist, they are motivated by ideology, political beliefs, or social causes rather than financial gain. And then some attackers are motivated by recognition, reputation, or just personal challenge. So these individuals may attack well-known targets simply to improve their skills or gain credibility within a community. Espionage. So espionage-focused attackers seek confidential or sensitive information rather than immediate disruption or profit. So maybe this is like corporate espionage. And this doesn't have to be as, like some James Bond, Jason Bourne type espionage. This is more like, hey, can we like poach somebody? Can we pay somebody? And you say, well, that's really cyber related. Well, it is, because when you're doing research and development, part of your cybersecurity function to protect the company is to say, hey, that our software, our technology is protected, right? It can't, we sign NDAs and things like that. But it could also be more related to a cyber attack. It could be that your corporate competitors are looking through your employees' LinkedIn's, looking at their personal Google Drives, looking at their personal GitHubs to see if they're actually releasing some technology that they use at work, okay? Another thing we're going to talk about is just resources, okay? So resources among these threat actors. So time is a resource. So attackers with limited time tend to use fast automated attacks and quickly move on if unsuccessful. So what we're saying here is think of more like a scripts kiddie. Downloading these scripts, downloading popular attacks, or becoming part of an active exploit campaign that's well known. That's quick, right? You don't need a lot of time for that. Attackers that do have a lot of time, that can be persistent and attack a single target with a year or 2 years, more than likely are going to be an APT, okay? So you need to kind of know that acronym, APT, Advanced Persistent Threats, or Advanced Persistent Threat Teams. Those are going to be our well-resourced, well-funded attack teams that have all the time in the world, okay? And typically that also is going to be correlated with the nation state. So as we were talking about with geopolitical motivations, nation state threat actors, we like to lump them into what's called an APT. An APT is usually funded by a nation state. Doesn't have to be, it's not like APT equals nation state, but typically advanced persistent threat teams or advanced persistent threat actor, an APT, is going to be well funded. Okay, money. So money enables attackers to purchase tools, infrastructure, and expertise. So well-funded attackers, they can do botnets, they can hire skilled developers and operate sophisticated command and control systems or C2 systems, with those huge botnets. Okay, capabilities. So let's describe capabilities of different threat actors. So capabilities describe, and this is like an umbrella term, right? The technical skills, the access, and expertise of a threat actor. So capabilities determine not just whether an attacker can succeed, but how difficult it will be to detect and stop. So what we're saying here is that if we're doing threat hunting activities within our organization, and we use different threat hunting models or frameworks like the Diamond Model of Intrusion, we use the MITRE ATT&CK framework, which we're going to go over in our lessons coming up, we need to determine their capabilities. So determine who the adversary is and determine their capabilities. This can be, based on historical knowledge. So we may know that, hey, they have the capability to attack our supply chain. They have the capability to create vulnerabilities. And once we start understanding their capabilities and where they may sit in our kill chain, then we can start better defending it and start having better blue team activities that are proactive against those threat actors. So supply chain. Supply chain access allows attackers to compromise systems indirectly by targeting trusted vendors, software providers, or service partners. Some advanced attackers are capable of intentionally creating vulnerabilities rather than simply exploiting the existing ones. And this is what we're kind of talking about, with an advanced persistent threat team. They're usually the guys, the gals, the teams that create the vulnerabilities that get assigned to CVE, not a team that just rides the coattails of it. Because, there are hacker teams that are just like, oh, there's a well-known CVE. Okay, there's an active campaign against it and a well-known way to exploit this vulnerability, now we can start targeting people, right? So with APTs, nation-state actors, they may be the ones creating the vulnerability, finding the holes or flaws in a system to do remote code execution or to create a persistent backdoor. Okay, attack pattern. So I have over here on the right, that's an image of something called the cyber kill chain created by Lockheed Martin. Attack patterns are not one-to-one correlated to this. This is just kind of an example of a well-known model that goes over attack patterns, okay? The reason I say that is because we're going to go over this like in an actual slide in itself, okay? So what are attack patterns? Attack patterns describe the common sequence attackers use to compromise system. This is essentially their TTPs. Their, the way that they attack, the way that teams historically have attacked. And it's not often we get a brand new APT on the scene. Sometimes we do, but in cybersecurity, a lot of these attack patterns do have historical data and heuristics and signature-based data to back them up. So these patterns often follow predictable stages such as reconnaissance, exploitation, persistence, lateral movement, and data exfiltration. Understanding attack patterns allow defenders to anticipate attacker actions and disrupt them early. So what we're talking about here is once we understand the flow, we understand the flow of how an attack would work. And honestly, looking at pen tests is a great way to understand an attack flow as well. But once we understand the flow, if we know that the first step is reconnaissance and then a social engineering attack to get an employee to fall victim to phishing, where in that cycle or those steps can we best attempt to stop that attack pattern? Where can we stop it? We can't stop open source reconnaissance. As much as we'd love to tell our employees don't post on LinkedIn, don't put anything online, we have to. We have to post the technologies we use in some organizations because that may be our selling point. Doesn't mean we have to give up key secrets, but at some point we're going to have some open source knowledge about our organization on there. So if we can't stop the passive reconnaissance, the open source intelligence research against us, then what can we do? Well, if we know that the next step is going to be a social engineering attack and a phishing attempt, we can try to stop that phishing attempt. We can say, hey, in this kill chain, I'm going to stop the phishing attack. So I'm going to put filters on my email, my email gateway, which is like Office 365. I'm going to do SPF records. I'm going to do DKIM and DMARC. I'm going to do training and awareness for my users to try to stop this attack pattern. And what we're doing here is threat modeling. What I'm describing to you is the threat modeling process in a very simplified format. And there are frameworks that can help us with this. So we have things like the Matter Attack Framework, the Cyber Kill Chain, the Diamond Model of Intrusion Analysis that we're going to go over to help us start to create this threat modeling component. All right, well, that was quicker than I thought. Okay, let's do our quiz. So we are at domain 1.4.1. Now I'm going to zoom in here so we can get a better view. Let me bring up my other tab I have open here when I'm doing these lessons. Okay, so question 1 of our domain 1.4.1 quiz. During threat modeling, a security analyst identifies an attacker who is highly skilled, well-funded, and primarily interested in stealing confidential research data without being detected. Which combination of characteristics most closely aligns with this threat actor? So they just want to steal confidential research data. They don't want to be disruptive. They don't want to, and they're not financially motivated. So that's not A. It's not an activist. And they're not looking for popularity or notoriety. So we're going to go with D. Espionage motivation with advanced knowledge and persistence. And that's because it's highly skilled and well-funded. Question 2. A security team is performing threat modeling for a healthcare organization that stores patient records and processes insurance payments. The team determines that the most likely attacker is financially motivated and has limited time and resources. Which attack behavior is most consistent with this threat actor profile? So time is limited, so it's not A, it's not long term. Manipulation of software updates provided by trusted And no, that's not it. That's not an attack behavior. Custom exploit development targeting 0-day, that will take a lot of time. So I'm going to go with B here. Automated phishing campaigns designed to deploy ransomware quickly. And when we say automated, you can go kind of buy this stuff like on the deep web or dark web. It's pretty easy. Or maybe you can get a local AI model and you can, jailbreak it, quote unquote, and get it to make malicious things for you. Okay, question 3. An organization discovers that malicious code was introduced into its environment through a trusted third-party software update. So, trusted third party, so we're thinking vendor, supply chain. The attacker bypassed perimeter defenses and affected multiple systems simultaneously. Which threat actor capability best explains how this attack was possible? So I'm going to go with C here, a supply chain access, because it's trusted third-party software update. So essentially we're saying somewhere in the supply chain, this is like software supply chain, not physical, that we got an update from a third party, but that third party was, it was infected, okay? So that's supply chain access. All right, 100%. Let's go, guys. Let's go ahead and take our first 10-minute break here, and then we'll get through domain 1.4 when we get back, okay? Okay guys, let's go ahead and get started again. So domain 1.4.2, given a scenario, perform threat modeling activities, frameworks. So in red, this is where we're going to go over here, the different frameworks that we have available to us. So the MITRE ATT&CK framework. So the MITRE adversarial tactics, techniques, and common knowledge framework focuses on how attackers behave during real-world intrusions instead of concentrating on vulnerabilities or assets alone. So the ATT&CK framework documents what adversaries actually do once they begin targeting an environment. And this screenshot here shows you the matrix. Okay, so the MITRE ATT&CK matrix. We can actually just go online here. And yeah, that's fine. We can just click here and we can look at the different matrices we have. So you see we have enterprise, we have mobile, and we have ICS, which is industrial control system. So that's that OT environment. So what we're looking at here, you may say, well, you know, what is this? What are we actually viewing here? So what we're seeing here is that there's a whole matrix developed for different types of attacks and historical knowledge and different advanced persistent threats that have done it and the way they've done it. So the tactics, techniques, and procedures. So let's say I'm worried about let's see one that's easy. Multi-factor authentication interception attack. So credential access attack. So I can see here the different APT teams that have done this. So APT 42, and then we can actually take a look here at this advanced persistent threat team and get some like historical knowledge about them. Has intercepted SMS-based one-time passwords and has set up two-factor authentication. Has cloned or faked websites to capture MFA tokens. So we can see there's an Iranian-sponsored threat group that conducts cyber espionage and surveillance. They start cyber operations through spear phishing emails and or Pine Flower Android malware. So we don't need to go too deep into this. I think you kind of understand how this can help us in threat modeling. So let's say I am an organization that is worried that I could be targeted by APT 42. For whatever reason, they attack my industry. It would tell you here, right? If they like have a specific industry they target. But anyways, you can kind of see how this can help us. It can start saying, okay, here's the techniques they use. And here it's saying they typically start cyber operations with a spear phishing attack. So if I know that an APT could be more or less doing phishing attacks against me, primarily to get, start the attack, to get a link, a step in the door, I know that's what I want to protect in my organization. And then I can start building a threat modeling in my organization to say, I use MITRE ATT&CK framework to determine my advanced persistent threat, who my adversary would be. And then I use that for the TTPs. And I can go to like the cyber kill chain and say, where can I stop them in their tracks? Or where is the most effective way I can stop them in their tracks when they attack my organization or enterprise? Okay, so MITRE ATT&CK is most effective when modeling threats against existing systems. It allows security teams to simulate how an attacker might move through the environment step by step, from initial access to achieving their final objectives. So they map existing controls to attack techniques. Defenders can identify gaps in detection, prevention, and response. So that's kind of saying how we can help us in threat modeling. Okay, this is one I haven't really used before that I kind of had to learn like when I was making the course, but CompTIA, Common Attack Pattern Enumeration and Classification. So we can go to their website here as well. Also sponsored by MITRE. This is the one I think I was saying yesterday. I was like, damn, it kind of looks like an old website. Like, they need to get Claude Code up in there to redesign this thing. But anyway, just another way to help us with threat modeling. And let's go ahead and just read the slides here to say what it's specifically going to help us with, because that's kind of the bullet points you need for the exam that you need to memorize. So the Common Attack Pattern Enumeration and Classification Framework focuses on common ways attackers exploit weaknesses in system design and implementation. So CAPEC, or CAPEC, documents attack patterns that describe the conditions required for an attack, the steps attackers typically follow, and the potential consequences. So unlike ATT&CK, which emphasizes attacker activity during intrusions, CAPEC is especially valuable during system design and architecture reviews. So architecture reviews is when we want to use this. Okay, the cyber kill chain model. This is going to be kind of what I've been talking about with like stopping an attack in its tracks. So the cyber kill chain kind of simplifies cyber intrusion, attack, and exfiltration and persistence or actions on objective in 7 steps. And in these 7 steps, the point of this model is to help you identify where you think you're most vulnerable or where you think you can stop the attack most effectively in your organization. So they say step 1 is reconnaissance, 2 weaponization, 3 delivery, and 4 exploitation. And then 5 installation. Somewhere in here, usually steps 1 through 5, is where you want to stop the attacker, that threat actor. Kind of like I was saying earlier, reconnaissance is hard. It's hard to kind of fully hide your email addresses and public things that your company is going to be doing. Like if you're heading to a conference, maybe some really sophisticated attacker can try to go work some human behind there or in that conference. High level, right, for SecurityX exam, this cyber kill chain is meant to help you determine in your organization the best place to stop the attack. If that's during the delivery phase or the exploitation phase or the installation phase. Think like installation phase, I can install XDR. During the delivery phase, I can do training and awareness and email filtering and things to stop the delivery from ever reaching my users. Exploitation, exploiting a vulnerability. So if I have known CVEs in my environment or legacy systems, I know what I need to do to stop those vulnerabilities from being exploited. Now, if this is talking about exploiting like the human element, a phishing attack, sometimes you can't just completely stop that, but you can attempt to. So it's kind of like you have to determine during your threat modeling structure or activities where you best fit in this cyber kill chain to prevent an attack, okay? Diamond model of intrusion analysis, another framework that can help us. So the diamond model focuses on the relationships between 4 core elements of an intrusion. The adversary, their capabilities, the infrastructure they use, so the infrastructure they use, which kind of is like also what do you have available where's your attack surface, right? So that's the infrastructure they use is also like your attack surface along with their infrastructure. And the victim they target, so the victim being you. So this is, I like to say you can use this in conjunction with MITRE and with cyber kill chain. Don't think of these frameworks as I'm only using this. You can use them together. The diamond model kind of helps you figure out who your APT will be exactly. So if I'm the victim, and let's say I'm the Ukrainian electrical sector or the Ukrainian ICS utilities infrastructure team, whatever that may be. I know it's pretty broad, but I'm saying that because it's a real world example of what the Sandworm team did for Russia during the invasion of Ukraine. But anyways, let's say I'm the victim. So who's my adversary going to be? Well, I know that I may have a direct near-peer adversary that dedicates their time, their efforts, their resources to attacking my critical infrastructure. So I figured out my adversary is the Sandworm team. Now I can use that to branch off to the infrastructure they would use. So they're going to use my OT environment, and maybe this is the tools they use. And I can look historically at what their capabilities are. So once I find out their capabilities are typically a phishing attack first, and then their specialty is, let's say, privilege escalation or remote code execution, I can then look back at my infrastructure or go to that MITRE attack framework or go to the cyber kill chain and start understanding where I need to start protecting and be proactive in my environments. So you can start using all these models together to do more accurate threat modeling. And essentially, the end goal of threat modeling is what? Reducing attack surface and being proactive in your monitoring. Okay, STRIDE. Let's go over this acronym STRIDE. So STRIDE is a threat modeling framework that categorizes threats based on what can go wrong within a system. And each letter represents a class of threat. So spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privileges. So STRIDE is system-centric and defensive in nature. It does not focus on attacker identity or motivation, but instead examines how system components could be abused. So this isn't a framework that says, oh, well, I'm running Windows Server 2022, I'm in the electrical sector, but my APTs don't usually attack Linux, so I'm good. This is saying, no. We don't care what sector, what industry you're in. We're looking at the system as a whole. Just here's a system, and here's where it could potentially be exploited, and that's it. So that's STRIDE. Okay, OWASP. the Open Web Application Security Project. This is another nonprofit, public, open source website and documentation and knowledge management base that can help you with protecting your web applications, your web servers. So here you have the top 10. This is usually like the top 10 web application attacks or exploits or vulnerabilities that it comes out with like every 5 to 6 years. OWASP. It's useful when threat modeling applications, particularly during development and testing. And remember, this is for web applications. So on the exam, if you see, what threat modeling do we have available to us, or what framework do we have available to us to help us protect our websites or our e-commerce platform, OWASP. Okay, now let's go over a couple different high-level things when it comes to threat modeling. So threat modeling with and without an existing system. So when a system already exists, threat modeling focuses on identifying current attack paths and evaluating whether existing controls are sufficient. So what we're saying here is let's say we already have some sort of defense in depth approach. We already have cybersecurity systems in place for our enterprise. We do threat modeling a little different. We say, hey, here's what we have. Let's try to match that with these frameworks, to match that to an APT, to match that to TTPs, to match that to where we can stop an attack from happening, okay? But when no system exists, threat modeling can actually help guide those securing decisions beforehand. Where, after, let's say, we're kind of we're in our growth phase of securing our environments, and what I mean by that is we're a small business, becoming a medium size, becoming a large enterprise. So as our IT systems develop and get bigger, maybe security wasn't initially part of the plan. And now we start securing, and now we start bringing in experts and hiring cybersecurity engineers. So their main goal is going to be, well, first let me just get my monitoring set up, get my scans set up, start getting into a life cycle of hardware refresh and updates and upgrades, and just start doing the little things. And then as we get more robust, as we become more proactive, then we may start hiring or start dedicating people, time, and resources to threat hunting and threat modeling activities. And that is when we have that existing system. But when we don't, and we do this initially up front, we say, hey, we don't have our web server farm made yet, or maybe we have an idea of a plan, and we're identifying that and integrating security into that first and before we deploy, and part of that is threat modeling, okay? So the goal of when there's no systems, existing systems, is to prevent vulnerabilities from being introduced by choosing secure architecture, implementing least privilege initially, and selecting appropriate authentication and authorization mechanisms for the initial build. Okay, let's go ahead and do our quiz. So we're at domain 1.4.2. Let's go to our lessons here. Go ahead and take that domain quiz. Okay. So question 1. An organization operates a mature enterprise network with centralized logging, endpoint detection, and an active SOC. That's a Security Operations Center. The security team wants to evaluate how an attacker would realistically move through the environment after initial compromise and determine whether existing controls can detect lateral movement and privilege escalation. Which threat modeling framework would be most appropriate for this analysis? Okay. So we have an entire enterprise, and we want to evaluate how an attacker would move laterally through our environment after they've already compromised us. So we're trying to determine how they would do it, not how to stop them, not the vulnerabilities in our environment. We want to know how they would do it or how they did it. Okay, and then determine whether existing controls can detect lateral movement and privilege escalation. So already off rip, I'm going to get rid of A, I'm going to get rid of D. Because A is just like that whole system narrative where it's like this system, let's look at these, what every letter in that acronym stands for. Elevation of privileges, denial of service, okay? So not going to be that. It's not going to be OWASP either, because that's just web applications, period. What makes me think it's MITRE is because it looks like this is trying to tell us we need to figure out TTPs, okay? If we didn't have this line here, how an attacker would. If we're just like, we want to see lateral movement or we want to determine lateral movement, maybe I'd go towards B. But I'm going to go with MITRE ATT&CK here. Let's read our explanation. So the MITRE ATT&CK is specifically designed to model adversary behavior based on observed attacks. Okay, so yeah, we were right. MITRE ATT&CK framework. Question 2. An organization wants to improve its ability to stop attacks early by identifying multiple points where an intrusion could be disrupted. So I'm already thinking probably like a kill chain. The security team is less concerned with who the attacker is and more focused on breaking the attack process at various stages, from delivery to command and control. Okay, so yeah. Which threat modeling framework best supports this objective? That kind of like put us on target there, right? That was kind of easy. Cyber kill chain. Cyber kill chain is, it pretty much damn near just made a definition for cyber kill chain, right? Where can we stop attacks in the various phases that they may happen? Okay, question 3. A software development team is designing a new web-based application that will handle sensitive customer data. No infrastructure or code has been deployed yet. The security team wants to identify design-level threats such as unauthorized access, data exposure, and privilege misuse before development begins. Which threat modeling approach would be most effective in this scenario? So it says web-based, but it's missing OWASP there. So that would have been my answer if it was on there. But we don't have infrastructure or code. Nothing's been deployed yet. But we want to identify design-level threats. We just want to look at an application and say, at the application, at the system itself, where could we potentially find vulnerabilities? So we're not looking at an attacker. We're not looking at where to stop a kill chain. And we're not deciding what our adversary is or who the victim is. We're just looking at the system itself. So I'm going to go with B here, stride. So remember, this is just looking at the system itself, right? It's a system-centric framework that categorizes threats based on what can go wrong within a system. Awesome, another 100%. Now let's move on to domain 1.4.3. Try to get through, trying to finish up domain 1 before we go on lunch, right? Okay, domain 1.4.3. Given a scenario, perform threat modeling activities, and we're going to go over attack surface determination. So now I've kind of been talking about this, like our attack surface. The whole point of threat modeling is to reduce our attack surface, and now we're going to figure out how to determine it, period. Okay, so attack surface overview. So an attack surface is the total collection of ways an attacker can interact with a system, whether directly or indirectly. This includes network services, applications, users, credentials, integration, cloud resources, and even business processes. So business processes is that big one cybersecurity professionals tend to forget. Like if we're talking to third-party vendors over an open line, like there's just so many ways that in the human element of it all, we could give away a lot of secrets. So in layman's term, guys, the attack surface is just your enterprise. It's every single IP resource and even some human elements, that's your attack surface. So everything involving and dealing with your enterprise is part of an attack surface. Okay, architecture reviews. So architecture reviews are foundational threat modeling because they define what exists and how it fits together. So what we're talking about here is, think about just a network design. When we try to look at the data flow from maybe a user application all the way to its backend database in our cloud, all the way to our on-prem employees and how it's providing it to our customers. That's an architecture review. So here we're trying to determine how everything fits together. If we have microservices running in the cloud, if we have a monolithic web architecture running on-prem, all of our network infrastructure, our container clusters, and all the technologies, credentials that are involved in that architecture, and seeing how, the big puzzle there. So from a threat modeling perspective, architecture reviews focus less on performance or scalability and more on exposure and trust. So really when I'm doing like an architecture review as a cybersecurity professional, I'm not really concerned from a threat modeling perspective, concerned if, this switch is high density ports with 40 gigs throughput. That's awesome. That's going to give us a lot of bandwidth. No. I'm concerned with, okay, I have that switch. it's sitting in this main distribution frame. Is that comms closet locked? Do we have, layer 2 security on it? And how does that switch interact with the rest of the enterprise? And is it leaving any holes that can increase our attack surface? Is there open ports on there? Do we have AAA running on there? Do we have port-based security running on there? That's what I care about. Is it talking directly to like a cloud service, or is it part of the data flow when our users are going up to the cloud? Pretty much how is it exposed? That's what we care about our architecture reviews from a threat modeling perspective. Okay, and then data flow analysis. The data flow analysis examines how information moves through a system over time. So if we're looking at this right here, this microservice. So maybe in our Azure Account 1, we have an application that's serving our clients, whatever that application is. Maybe it's a ERM, Enterprise Resource Management, or it's custom, whatever it is, doesn't matter, it's an application, okay? Here's how that application works. So maybe we have microservices, we have a database back here, we have an Azure function running the back end, and then an API gateway for access. And then maybe right here, not seen as like a NAT gateway, network security groups and ACLs, and then a public IP right here that our client accesses this application. And maybe there's DNS involved. That's our data flow analysis. Trying to understand the data flow, to understand where we might need protection, or enforce some better authentication methods as well. And then, what's exposed essentially is what we're saying. I don't need to go down the list of, could it be an API? Could it be unencrypted connections? Could it be we're not logging properly? Okay, trust boundaries. So a trust boundary represents a transition point where the level of trust changes. This used to be a classic cybersecurity, like network security routine where we'd have a firewall and the inside network would be trusted, the outside network would be untrusted, and we'd say, oh, it has to all come through here, so as long as we protect this untrusted interface to the internet, we're safe. But now these trust boundaries are a lot more complex with our hybrid models and our cloud deployment models. So threat modeling has become more complex as well when determining where our trust boundaries are. Just because a user is inside our enterprise doesn't mean they're not reaching out to the internet, and doesn't mean we don't have trust boundaries at all these different places in our cloud environment. There could be some SaaS applications, there could be Intune managed devices, we could have on-prem Active Directory that's doing authentication, so many different places that could be a boundary from our protected resources or subjects like our users, file servers, to an object, right? An object being that SaaS application in the cloud, whatever the case may be. So that becomes part of our threat modeling as well. Now, code reviews. So reviewing the actual code that may run our systems or applications. So traditional code reviews focus on correctness and maintainability. Threat modeling driven code reviews focus on abuse. So the question is not whether the code works as intended, but whether it can be made to work in unintended ways. And what we're saying here is that we need some sort of analysis. We need to do some sort of static or dynamic code analysis to identify any exploits, potential vulnerabilities, or potentially unsafe third-party applications or integrations that are going into our code. Okay, user factors. So the hardest part of threat modeling is the user, is the employee. It's just something you can't predict. You can put them through all the training and awareness that you want, but doesn't mean they're not going to fall victim to a phishing attack. So what can we do? In our threat modeling, we can just kind of chop this up to, hey, when we're protecting our organization, we're going to be proactive in designing education and awareness, but we have to have expectation management that a user may fall victim to a phishing attack. It's probably going to happen. So we need to have systems in place to protect us. XDR on the user's machines, mobile device management on a user's like a laptop or their company phone, email gateway and filters, session monitoring. Maybe we can monitor sessions directly, actually do some TLS decryption and then inspection on HTTP at like our firewalls, which is commonplace now. We can enable AI learning or an LLM to determine user behavior, and when something deviates from a normal user behavior, we can address that either with just a ping to the cybersecurity team or say, hey, we've noticed that you're working at 2 a.m. Is that you? And they can explain why, or that helps us determine that, oh no, it's actually data exfiltration happening. Okay, organizational changes. So let's go over this. This is kind of like the boring stuff here, but something that we have to be aware of if we're ever in this position. So mergers. So a merger combines previously independent organizations with different security cultures, technologies, and risk profiles. So there's new network connections, there's new systems, new applications interacting with each other, and now we have to share trust with another organization's IT team. So what we're saying here high level is that when there's a merger, we have to combine efforts and combine IT systems, and we may not have the same security policies or standards. So something we have to be aware of. Now, acquisitions may be a little different. Acquired organizations often bring legacy systems, undocumented access paths, and unsupported software. Because why get acquired? You may be this kind of is like saying you got acquired because you were maybe starting to fail as a business, but that's not how I look at it. You may get acquired just by a larger company and you get rolled up, and more than likely you have to give up your systems, okay? So when we're bringing over, though, that company, we need to make sure and vet that their data is going to be safe for us to integrate with. And essentially just take control, right? Okay, divestitures introduce risk when access is not fully removed. Former employees, system, or partners may retain credentials, VPN access, cloud permission, or shared services. So what we're saying here is like when we get rid of people, we get rid of departments, or we divest from something, we do proper offboarding. Okay, then staffing changes. So staffing changes affect security by altering who has access and knowledge. So when we move people around to different departments, just know we have to do, least privilege. We have to do role-based access control. And we have to make sure we offboard properly or get rid of permissions and add permissions effectively and properly in accordance with our security policy, which is always going to be like least privilege and role-based access control. Okay, enumeration and discovery. So threat modeling is impossible without visibility. So we can't begin to reduce attack surface, build some threat modeling tactics and techniques and threat hunting techniques unless we know what we have. And we have to know where it sits. Is it internal? Is it external? Do we have remote workers over here? So internal and external assets. Externally facing assets are commonly targeted for initial access. So this is something that's public facing. And then internal assets are targeted for privilege escalation and lateral movement. What we're saying here is essentially your external asset more than likely is going to be the touch point. It's more than likely going to be the place that attackers try to get to first to then laterally move to the internal assets to then do privilege escalation and start building back doors. Third-party connections. So third-party services extend trust beyond organizational boundaries. Threat modeling evaluates how compromise of a vendor could impact internal systems, data, and availability. This is kind of like what we've been talking about, that supply chain, that vendor vulnerabilities. Unsanctioned assets or shadow IT. So sometimes our users may not feel supported and they feel like they got to bring in extra IT or extra software to help them get their job done or to be more effective. We call that shadow IT. So that is unmanaged risk, right? So, it introduces unmanaged risk by essentially bringing in a whole new application that we have no visibility into, so we can't even begin to protect it. And now that's a touch point, that's a boundary we don't know about. Cloud assets. So this is something that it should damn near just start being enterprise assets at this point. The cloud is used for everyone, but I get why they make it its own little asset, because it's a provider, right? It's a vendor essentially. When you work in the cloud, you're placing your company's data into another organization's data center. That's what we're doing when we do operational expenses and deploy architecture in the cloud. That's what it is. So cloud environments are dynamic and ephemeral, meaning assets can be created automatically, misconfigured instantly, and exposed globally, which I know a little bit about that. That's happened to me. Compare this, contrast this with on-prem, where I have a server, I own that server, I do the power forward, I do the lifecycle maintenance for it, but in the cloud, with a single Terraform script, I can generate 4 new VMs, new containers, new storage accounts, and immediately expose it, right? So with cloud assets, we actually want to be a little bit more careful with our protection in our IAM than we would be with our on-prem. Public digital presence. So publicly available information provides attackers with reconnaissance data. That's job posting, social media, DNS records, and code repositories that if you're hosting it publicly, could reveal technologies, roles, and how your architecture is working. Okay, last slide here. So abuse, anti-patterns, and attack trees. Just some more like threat modeling terms. So abuse cases describe how legitimate functionality can be misused. This attacker-centric approach reveals weaknesses that functional testing does not. Anti-patterns represent known poor design choices that repeatedly lead to compromise. Then attack trees and graphs model how attackers achieve objectives through sequences of actions rather than single vulnerabilities. Okay, let's go do our quiz now, and then we'll take another break. I've been yapping for a minute. So we're at domain 1.4.3. Okay, question 1. An organization recently acquired a smaller company and quickly connected the two networks to enable shared access to applications. No formal security assessment was performed prior to the integration. From a threat modeling perspective, what is the primary risk introduced by this action? Okay, so increased likelihood of denial of service attacks. Maybe that could happen because now two organizations, right? Immediate compromise of sensitive data? No, it won't be immediate because it didn't say there's lack of encryption. Expansion of attack surface through inherited vulnerabilities and implicit trust. I'm going to go with that. I didn't even need the last couple words here, implicit trust, whatever. It increased attack surface. That's what it does when you acquire an organization and they have their own IT assets. Okay, question 2. During a threat modeling exercise, a security team maps how customer credentials move from a web application to back-end services and then to a database. Which threat modeling activity is the team primarily performing? That's data flow, right? That's data flow analysis. Yep. Okay, question 3. A developer argues that user input received from an internal application does not need validation because the source is trusted. Ooh, horrible zero trust architecture. From a threat modeling perspective, why is this assumption dangerous? So trust boundaries exist everywhere. Even if it's internal, like if we're in a zero trust architecture, or we try to be at a zero trust architecture, one of the key principles is never trust, always verify. Even if that subject is in your internal network in a trusted VLAN with trusted GPOs, all on-prem, when it tries to access an object like a file server, zero trust says you still need to re-authenticate them or that subject, whatever that subject may be. So trust boundaries exist everywhere. It doesn't matter if it's external or internal. So I'm going to go with B here. Trust boundaries still exist even between internal systems. All right, awesome. So we're going to take another little break here. We'll take 10 minutes, and when we come back, we'll finish up domain 1. Domain 1.5.1 summarized the information security challenges associated with artificial intelligence adoption. So now we're going to talk about AI in the SecurityX course. So we're going to go over threats to the model and AI-enabled attacks. So now, as our landscape changes across industries and AI becomes more prominent, we need to understand the dangers that it can present to cybersecurity functions within our organization. Did you guys hear about that? I wonder if I look up hack, meta prompt AI attack. Let me show you guys this. So hackers tricked Meta's AI support bot to infiltrate a lot of high-level Instagram accounts. So they call it a prompt injection attack. That's we used to have LDAP injection, SQL injection attacks. Well, we still do, not that we don't anymore. But anyways, that's a new one for LLMs, large learning models, is prompt injection. We just look at it. I hate The Guardian, but we'll just look at it. Pretty crazy, right? That their chatbot ended up doing that for them. Okay, a little disclaimer. Yeah, all the images in this slide are AI. I don't use AI in anything else. Just to kind of show you guys, AI. I'm not an AI hater. I use it I use it every day, damn near, for my day job, helping me write stuff. But anyways, let's move on. Okay, AI systems rely on large volumes of data to function effectively. This data often includes sensitive information such as PII, financial records, behavioral data, and protected health information. So what we're saying here is that if you're going to put that kind of information into a LLM, make sure it's secured the same way that you've always had to secure that information. Don't let it go across the wire into an untrusted environment unprotected. If you're using a public instance of a large learning model, you just straight up putting people's PII into ChatGPT or Claude Code, on your personal account, that can be an issue, right? Same way with the cloud. When we started working in the cloud and it was a public model, we started putting all of our company's sensitive information into a cloud that we didn't really own. So there's many ways to go around this, or not really to go around this, to be in compliance with our legal and privacy implications. You could host a AI large learning model locally as well inside the organization. Okay, potential misuse. So AI technologies are general purpose tools that can be repurposed for unintended or malicious uses. So while organizations may deploy AI to improve productivity or security, attackers use the same technology to enhance fraud and deception. And really the deception is the big one. Well, fraud as well, but with deep fakes, with images, AI can get a little scary with that, making something look very realistic. And to mimic language, right? To mimic someone, how they would send an email. So think about if you could capture the way a CEO writes his emails, and you feed that to an LLM, then you tell that LLM, can you make me an email that sounds like this person? And then you use your phishing domain to do business email compromise. That could look super legit. Okay, explainable versus non-explainable. So AI models can generally be categorized as explainable or non-explainable. Explainable AI models allow humans to understand how inputs are transformed into outputs. Non-explainable models, often referred to as a black box model, produce results without revealing the reasoning behind them. Okay, moving on. Organizational policies. So many organizations adopt AI tools without formal policies governing their use. So this is kind of what I was talking about, where you may just start enabling large learning models on all your network devices, at your firewalls, on your SIEM. So you have all these AI models within your organization, and you don't know where they're storing data, how much compute you actually needed, and where they're sending your data off to, if they have to reach back to somewhere. So as an organization, you're going to have to eventually start structuring AI in a secure way if that's your concern. Your concern is data leaks or data breaches or misuse of PII, PHI, financial records. Okay, threats to the model. Prompt injection, what we just talked about. So prompt injection attacks. So prompt injection occurs when an attacker crafts input designed to manipulate an AI model's behavior. This can cause the model to ignore safeguards, disclose sensitive information, or produce harmful outputs. So essentially what we're saying here is when we produce a customer-facing AI that's meant to take user inputs, there's supposed to be guardrails against it, what you can and cannot respond back to as an AI. But obviously, It's meant to be like self-replicating. It's meant to think on its own. So those guardrails aren't always 100%. That's when we have prompt injection attacks, where you can prompt that AI and trick it to go against its set guardrails. A little scary, right? Okay, insecure output handling. So AI-generated outputs are often consumed by other systems, displayed to users, or used to make automated decisions. If outputs are not validated or sanitized, attackers can exploit them to inject malicious command scripts or data. Okay, so training data poisoning. This is an attack where you may be feeding a custom, well, not say custom, let's say a on-prem large learning model that maybe you're setting up to do behavior analysis, to do heuristics-based analysis, so you can discover anomalies. Really common use case. But to do that, you have to train that model on what your behavior baseline is. And we're talking about this organizationally. So if our users come in from 9 to 5, that's where we see our peak network traffic, our peak concurrent traffic to certain websites. That's the normal behavior. A large learning model or an AI-enabled SIEM, firewall, whatever the case may be, learns that and now can detect anomalies. So all of a sudden we start seeing, huge amounts of data leaving the network at 1 a.m. That goes against the norm. It can then take action on that by alerting us, preventing it, whatever the case may be. But it needs that solid baseline. It needs that accurate baseline to do that. So an attacker could potentially and purposefully poison the training data, make it seem like that's normal to exfiltrate data at 1 in the morning. So pretty much if I enable my large learning model to learn 24/7 about my network traffic, and already there is persistent data exfiltration happening, well, then what, right? Then it's tainted. So it can never detect data exfiltration at that time because it thinks it's normal. Okay, model denial of service. So AI models often require significant computational resources to process requests. It's just another, as technology changes, a lot of things stay the same. A denial of service attack in the 2000s is the same as it is now in 2026 against AI. Just overloading resources. That's it. That's model denial of service. And with AI, it's not just network, it's more like the computation behind it, your compute resources, your GPU, CPU, things like that. Supply chain vulnerabilities in AI. So AI systems frequently rely on third-party components such as pre-trained models, open source libraries, cloud platforms, and external APIs. If any component in this supply chain is compromised, attackers may introduce malicious functionality or hidden backdoors. Same as any supply chain threat. Okay, model theft. So model theft occurs when attackers attempt to steal or replicate proprietary AI models. Model inversion attacks. Model inversion attacks attempt to extract sensitive information about a model's training data by analyzing its outputs. Okay, insecure plugins or deep fakes. So insecure plugins and integration design. So AI systems that interact with plugins, scripts, or automation tools may execute actions based on AI-generated decisions. So what we're saying is when we're designing an AI model to, like an agent, like an AI agent, to be proactive in our enterprise, to detect, to monitor, and to prevent any malicious intrusion, we have to make sure that we're designing it securely. So if we're putting in plugins that reach out to, like, let's say a third party that we don't think is secure, then the AI could be, getting those insecure plugins into its model and then proliferating that malware. So deep fakes and impersonation, kind of what I talked about social engineering. So attackers now have it super easy with faking voices, faking someone's language and how they type and write, and just real deep fakes. So the phishing attacks have actually become more prominent as technology moves on. I get SMS messages all the time with legit looking websites. It made it easier to copy websites, to clone websites. So deepfakes and impersonation are just going to be harder and harder to detect because of AI advancements. So AI-generated digital media and interactivity. So AI-generated content can be interactive and adaptive, allowing attackers to personalize scams and respond dynamically to victims. Essentially just what we're saying, that social engineering has become actually a little bit easier to conduct with AI. Okay, AI pipeline injections. So AI systems rely on pipelines that include data collection, pre-processing, training, deployment, and inference. So at any of those stages when building our AI pipeline to produce outputs for our users, inputs, if we inject something into that pipeline, it could give us a false output or potentially create some malware. And then AI enhanced social engineering, just what I kind of talked about already, don't need to talk about it again. And automated exploit generation. It's so easy now to automate reoccurring attacks. And what I mean by that is, if I'm using AI to generate social engineering attacks, from a single prompt, I can generate thousands of different prompts for social engineering, thousands of different emails, thousands of different smishing attacks, all from a single prompt. Okay, let's go ahead and do our quiz. So we're at domain 1.5.1. Okay, question 1. An organization deploys an AI-powered customer support chatbot that integrates with internal systems to retrieve account information and perform basic actions. During testing, security analysts discovered that carefully crafted user inputs can cause the chatbot to bypass content restrictions and expose internal system details. Which information security challenge is most directly responsible for this risk? So it integrates with our systems, and crafted user inputs can cause the chatbot to bypass its guardrails, its content restrictions. That's prompt injection. Literally what we just saw with this one right here, which is just so crazy, right? That someone just took the time to chat with Meta's AI, just chat, just type back and forth to eventually get them to release passwords and give you access to your Instagram account. Just crazy. Crazy. And then the companies will lay off 30,000 employees. And then we get these type of shit. Anyways. Okay. Question 2. A financial organization uses a complex deep learning model to automate loan approval decisions. Oh, that's good too, right? When you take the human element out of things, for things like that, which is happening all over. When a customer challenges a rejected application, the organization cannot clearly explain how the AI system reached its decision. This creates regulatory and legal concerns. Which AI-related challenge best explains this issue? So that's going to be explainable versus non-explainable models. Question 3. An attacker repeatedly queries a proprietary AI model exposed through a public API and analyzes the responses over time. Eventually, the attacker is able to recreate a functionality, a functionally similar model without ever accessing the original source code or training data. So they just stole the model. That's like what DeepSeek did, right? Which threat to the AI model does this scenario describe? Which technically isn't illegal. This is going to be B, model theft. All right, 100%. Okay, guys, let's go ahead and go back here. Let's go ahead and do domain 1.5.2. A little bit shorter here, be quick, and then we can get started on domain 2.1. Domain 1.5.2 summarize the information security challenges associated with artificial intelligence adoption. So this is going to be risk of AI usage and AI-enabled assistants / digital workers. So over-reliance. So over-reliance occurs when users place excessive trust in AI-generated outputs without adequate validation or human oversight. So this is like, using a Claude agent to do everything for you. Nowadays, if you're just like coding, doing simple tasks, you need it to, so I know some people that do this, you need it to purchase things for you, so you give it its credit card information. To me, that's over-reliance. But when we're talking about from a enterprise or cybersecurity perspective, over-reliance is just meaning us losing the ability to know when that AI is generating the wrong outputs. So it can be biased, it can have misleading information. So we just need to be aware of that as a security team, that if our main way that we validate security incidences is with trusted information, trusted tools, we need to be make sure we have the right guardrails against our AI systems. Okay, sensitive information disclosure. So AI systems often require access to large data sets to function effectively, which increases the risk of sensitive information disclosure. So this again is just going into our compliance, our governance, kind of going back to like yesterday, going over our first few PowerPoints. So disclosure, we can't have it disclosing financial records, health records, and PII. So disclosure to the model occurs when users input sensitive or confidential information into an AI system. And there's also that user awareness as well, telling our users, hey, do not put company information into your personal AI, your personal ChatGPT account. Excessive agency. So excessive agency refers to granting AI systems too much autonomy or authority without sufficient controls. Then access to permission and guardrails, kind of what I've been talking about this whole time. So AI assistants often require access to systems, databases, APIs, so like giving your API key to Claude, right? And internal tools to function. If access controls are poorly designed, AI systems may receive permissions beyond their intended scope. This violates the principle of least privilege and increases the risk of data exposure or system compromise. So like I've talked about, as much as technology changes, a lot of our cyber principles don't. We've been doing least privilege since we've had different types of service, admin, and user accounts. We've always kind of done least privilege even before it was put into a NIST special publication of an actual principle that was described. AI is no different. AI, we also have to intentionally do access control with it as well, like it's its own user, that it's its own service account. Okay, guardrails. So guardrails are technical and policy-based controls that limit what AI systems can access, generate, or act upon. So data loss prevention. So DLP, again, has been around in cybersecurity for a while now to stop data exfiltration, to stop you from plugging in USBs. So traditional data loss prevention solutions focus on endpoints, networks, and email. But AI introduces new data flows that can bypass existing controls. Users may copy sensitive data into AI prompts, or AI systems may generate outputs containing confidential information. So disclosure of AI usage is an important security, governance, and ethical consideration. Users and customers may not realize when AI is involved in processing their data or generating responses. Honestly, I don't know. I kind of dislike they put this all into one domain, 1.5. This is kind of my personal opinion coming in now. All they could have said for the AI section is make sure you have proper guardrails and make sure you don't disclose sensitive information, like tell your users, and if you're deploying it, don't give it access to your API keys. That's not good cybersecurity. And we could have been done with this section, right? Like all this other stuff is like almost like an ethics course in AI that isn't related to your day-to-day in cybersecurity. If you're enabling AI in your networks, do not upload all your sensitive information to it and try to put guardrails. But can you really put guardrails unless you create your own model? We all use the same OpenAI, Gemini, and Copilot code, even if we wrap it in our own stuff. So anyways, like our Gen AI that we use on our Nipper, right guys? I mean, I could post an entire config to there and it's classified as CUI, so whatever. But if I put passwords in there, who knows where that's getting, processed in the back end? Is there some cloud-based service that's giving me all my compute resource and all of a sudden that's holding all my configs passwords? Anyways, I just feel like it could have been wrapped up, This section was, hey, do you trust AI? Okay, give it access. If you don't, then treat it like you would a normal user. Privilege, like access controls, principle of least privilege, DLP, Anyways, I'll keep my personal opinion out of it. I don't really like AI, if y'all can tell. Even though I use it, I kind of wish it just wasn't around. But all right, question 1. An organization allows an AI-powered digital worker to automatically modify firewall rules and deploy infrastructure changes without requiring human approval. Which security concern does this situation most clearly represent? So we allowed an AI-powered digital worker to automatically modify firewall rules. So that is excessive agency of an AI system. Question 2. A developer copies internal configuration files containing API keys into a public cloud-based AI chatbot to troubleshoot an application issue. Which type of AI-related information security risk is most directly involved in this action? So we copied internal configuration files of our API keys. Oof. So that's disclosure of sensitive information to the model. Question 3. An organization deploys an AI-based security assistant to help analysts triage alerts and recommend remediation steps. Over time, analysts begin accepting the AI's recommendations without validating the findings or reviewing supporting evidence. Which information security risk does this scenario best illustrate? That is going to be B. Over-reliance on AI-generated outputs. All right, 100%. We're gonna just take a 5-minute break here, guys. Just a quick 5-minute break, and then we'll get started on domain 2, okay? I'm gonna drink some water and give my voice a quick little rest. Okay, welcome back everyone. Hopefully you all had a good lunch. We're gonna jump right back into it by going over domain 2.1.1 and giving a scenario, analyze requirements to design resilient systems. And we're gonna go over components, availability, and design integrity. So this is just gonna be one objective in domain 2.1, and we're gonna go over all these following exam objectives. So component placement and configuration. So now we're gonna dive into kind of network appliances. So what kind of network or server-side infrastructure do we have in our environment? What does it do? What do we need to be aware of as a cybersecurity professional? And how would we place it? And also, how would we configure it to make it resilient and to be a benefit to our cybersecurity defense in depth approach? So a firewall is security control that governs how traffic moves between networks. So, we say everything in the perspective of a cybersecurity professional. We say it's a control. As we know, it's a physical piece of hardware that we deploy and manage as network engineers. But its core function is to enforce security policy. That's the core function. Even though most firewalls nowadays will do NAT, will do VPNs, will do TLS decryption, will do some flavor of SD-WAN, the core principle of how it works for us as cybersecurity professionals is that it can do IDS, IPS, it permits and denies, and nowadays it's AI enabled to do that behavior analysis. And then in resilient systems, firewalls are usually not in a single location, and they're usually not just a single device. A lot of times we have active-active or active-passive pairs for our firewalls. Okay, what is an IPS? So intrusion prevention system is designed to detect and then actively block malicious activity as it occurs. Don't need to dive too deep on this. We start learning about IPSs all the way back in like A+. So IPS does exactly that first sentence. It detects and then actively blocks malicious activity as it occurs according to how you tune and build that IPS. Now, an IPS system is really no longer like a dedicated hardware appliance. It's going to be built into things like your firewall. So, I have Cisco ASA on my environment that I manage. We don't have IDS, IPS running on there. I could. It's like a plugin. It's like an additional feature that can be part of that firewall. Now, important thing about IPS and IDS solutions is our flagging and our tuning. So when I talk about alert tuning, what I'm trying to say there is that we don't want too many false positives or false flags on an IPS. Way more importantly, we don't want it on an IPS because IPS is intrusive. It could potentially block traffic. So we have to configure it in a way, its behavior, on how, what traffic do we determine to be severe enough to actively block without administrative intervention. Because that's kind of the whole point, right? An IPS is to block traffic for us that we deem is not safe. Long story short, we just got to make sure that we're doing it appropriately and we're doing our tuning correctly. And then an intrusion detection system, it's going to do the exact same thing minus the blocking. Mainly an IDS is there to alert us. And how we set up our alerts is very important. Do we send emails based off of severity? Do we send a phone call to the on-call technician based on the severity? And how are we detecting? We could be in line or it can be out of bound detecting. As you see here, I could have the IDS sitting here on my firewall, or I could be mirroring all traffic coming in and getting it sent over here, and that could be an IDS solution. Main point of IDS, it gives you visibility though. It gives you visibility and generates alerts for you, and you also tune those alerts and how you want them sent to you and when they should be sent to you, you being that SOC analyst. Okay, vulnerability scanners. Vulnerability scanners are a huge part of our overall defense in depth approach to being proactive and remediating exploits and vulnerabilities in our environments. So a vulnerability scanner, its pure definition, is a tool used to identify exploits or weaknesses in systems before attackers exploit them. This could be a scan for well-known exploits based off that operating system version or firmware version. It could also just be a vulnerability scanner to alert you when there's not proper hardening done, like unnecessary services, open ports, and services. Vulnerability scanning management is something that we have to think of as a cybersecurity director level in the SecurityX on how often we want to scan and how that scan is going to help us implement remediation steps. The overall goal, though, is to understand what risks are in the environment so that you can address them. And up here, we have our Nessus scanner. That's what I'm used to building in our environments, a Nessus scanner. Okay, a VPN. Let's quickly go over a VPN. Again, kind of almost like a layman's term. Now everyone knows what a VPN is, but how do we use it in our environments? When I say our environments, I mean enterprise. Is we have remote workers and site-to-site. So we have remote access VPNs that are going to be client-based installed software that is then going to connect to a VPN concentrator. When you guys take your NIPR computers home, you do exactly that. You have a Cisco AnyConnect VPN. Another one that I use in my environment is Palo Alto Global Protect. It's just a remote access VPN that's running on a Palo Alto service or firewall that I can give out a VPN client software solution or tunnel config to anyone. They can install it on the Windows computer and they can get access into the network that way. And then we have site-to-site VPNs that are going to connect to distinct sites. So think Office A over here in like Phoenix and Office B over here in New York. We can connect our local LANs on that private IP space over this VPN site-to-site solution. VPNs will also offer some privacy and encryption and authentication along with it. Most common ways to do VPN security, the technologies for VPN security, are going to be TLS or IPsec. And we can do authentication with pre-shared keys, some sort of multi-factor authentication for our remote workers, or some certificate-based solutions for both site-to-site and remote access VPNs. Okay, network access control. So NAC is port-based security for your switch, for your local devices that are going to authenticate clients. So let me take a step back, right? So what we mean by this is that a network access control solution determines who or what is allowed to connect to the network. NAC solutions evaluate devices based on identity, compliance, and security posture before granting access. What you see in a typical enterprise solution when it comes to network access control, like let's say you have Wi-Fi, is you'll have that wireless access point configured for WPA 2 or 3 enterprise mode. And that enterprise mode is going to use technologies or AAA technologies like Radius or TACX along with 802.1x to take that client's credentials, whatever that may be, CAC, a certificate on the actual laptop, phone, or desktop, and then send it off to an authentication server running Radius or TACX. And then that authentication server is actually going to grant them access to the network. Okay, WAF, a web application firewall. This is specifically designed to protect web applications from well-known web attacks. Think like a web application firewall sitting in line in front of your web application hosted in the cloud, maybe a part of some like protective service that the cloud offers for like VMs or your cluster containers that are hosting web applications, and it's inspecting HTTP traffic. So it's going to have to do some flavor of DLS decryption to actually look into a hypertext transfer protocol to determine if you're being attacked using a well-known web application attack, like SQL injection, cross-site scripting, cross-site request forgery. And if it determines that there is an attack present in that HTTP traffic, it's going to reply to that attacker with the forbidden, pretty much a 400 error saying, we're not going to allow you to actually connect to our web server anymore. Did I skip a slide? Oh no, here we go. Okay, a proxy server. So there's two types of proxy servers. We're going to have a forward and reverse proxy. They're going to do almost the same thing. Their core functionality is going to be to give you some, be a proxy. And what we mean by that is it's going to be doing NAT, network address translation or port address translation. It could also be doing packet inspection for us. So it could be doing URL inspection or actually gain visibility into the user activity, also doing some sort of flavor of TLS decryption, and could prevent traffic from leaving or coming into our network. So you look here at the forward proxy, we have our users sitting here on a private IP space. That forward proxy is going to do NAT or more than likely PAT, port address translation, and it's going to send that user traffic off to the internet. It could also be configured to actually inspect that user's traffic as well. So it could take that user's traffic end to end, like this user talking to this web server over here, do some URL inspection, do some TLS decryption, and actually inspect that packet, and then have some filters put in place, so permit or deny filters. Reverse proxies do pretty much the same thing, except it's going to be sitting in front of the web server farm instead of the forward proxy, is going to be sitting client side, okay? So that reverse proxy, you're sitting in front of your web server farm. Now this could be your cluster of containers running web applications, whatever the case may be. And when users go to, navigate to this web server, the reverse proxy is actually the one with the public IP that's probably going to have the DNS A record entry that users are connecting to when they build their packets. And then it's going to translate that traffic to the private IP space over to the web servers. So we're hiding our web server's actual IP identities on the internet. And then we could also be doing some sort of TLS decryption and packet inspection there as well. So proxies still are a dedicated appliance. Again, with the way kind of security is going now with our more robust hardware, a firewall could do all this just the same, right? Okay, API gateway. So an application programmable interface is an API is what gives us access to databases, backend applications, or to do requests and calls on some sort of service. So if we have a public API or an API gateway, what is the potential there for a cybersecurity attack? If we have a public API gateway where developers, users, other applications are making API calls to it to reach our service behind it or our database behind it, whatever it may be, we open ourselves up for a denial of service attack. It's an API denial of service attack. That's what these API gateways are exposed to. So when we build API gateways, it's important for us as cybersecurity professionals to ensure we have some of the basic cybersecurity controls applied to it, like authentication, authorization, rate limiting, and of course input validation to protect us against those common injection attacks that could be against a web application, can also be used against our API gateways. Now it's an API gateway because it's usually public facing. So if we have some sort of back-end web service, imagine a cloud around here, right? Imagine a cloud and you have all these microservices. It could be database, it could be back-end functions, this could be front-end web application. If we have developers that need to talk to it, we may have a public API gateway there because they may need that public IP, maybe they're, whatever the case may be. So when we have that API gateway public, we need to have the same protections that we would against like a web server. Okay, taps and collectors. So network taps are hardwares that provide a copy of network traffic without interfering with it. They are used to feed into IDS systems, different monitoring tools, or forensic systems. That tap could feed something into like a collector, then that collector could be sending all that information off to like a centralized place where then we can inspect it and monitor it. Now a collector in general though, just gathers logs, telemetry, and security events from multiple systems. A well-known collector or aggregator is like a SIEM system, a security information event management system, something like Splunk or Azure Sentinel. But collector, we're just kind of using like a broad term here. This is just any device that collects logs, collects events happening in our environment. That's a collector. Okay, a CDN. A content delivery network distributes content across geographically dispersed servers. CDNs improve performance, availability, and resilience by serving users from locations closer to them. From a security perspective, CDNs absorb traffic spikes and protect against distributed denial of service attacks by filtering malicious requests and offloading traffic from origin servers. So just imagine, we have our main server over here on the west coast of California, and we want to service customers all around the world and give them a nice user experience by not making the website load, longer than 2 to 3 seconds. Everyone wants things very quick now. That's kind of just the environment we're in. So we may offload some of that into a content delivery network where we cache some of our files, our front-end files, or even back-end files to servers all across the world. And then that user closer to that CDN will hit that CDN first, HTTP request and receive all the files cached in that CDN, and still may reach back to this server for more of the back-end logic for that web application, but the user experience is going to be a lot more seamless and faster with the CDN. All right, high availability in cybersecurity also relies on our network being highly available, and one of the ways we can do that is with a load balancer or by implementing load balancing techniques. So load balancing is a technique used to distribute workloads across multiple systems so that no single component can become overwhelmed. All that to say, a load balancer, like let's say F5 load balancer, maybe Zscaler, is used to take incoming network traffic and distribute it out to its destination appropriately so that systems do not get overwhelmed. This helps protect us against denial of service attacks, and it also creates a need to have consistency across our back end. But essentially, if we're just looking at what a load balancer does for us from a cybersecurity control, it gives us resilience. It offers us resilience. It helps us against denial of service attacks, and also helps us when we have those traffic spikes. Okay, recoverability. So recoverability refers to a system's ability to restore operations after a failure, attack, or other disruptive event. This is another broad term saying, as cybersecurity professionals, do we have certain controls, policies, and the technologies in place to make sure that our key infrastructure can come back online in case of any sort of disaster, whether that be an attack, a natural disaster, a power outage, or even if it is getting overused, a resource, or organically, just maybe an uptick in customers, legit traffic. So key components we have to worry about recoverability without diving deep into the different technologies that make it happen are backups, snapshots, replications, and of course, recovery procedures, kind of getting into, again, our policies and frameworks and SOPs on how we could do data recovery or system recovery. Interoperability. Interoperability is the ability of different systems, platforms, and services to work together effectively. So in a robust enterprise that is worried about vendor lock-in, that wants multiple ways to accomplish something using different vendors and technologies so we have no single points of failures, interoperability is very important. We want to make sure even if we are entering into a multi-vendor environment between our sites, not having a consistent baseline of hardware, we need to ensure that across the vendors, technologies are interoperable. Geographical considerations. So when we're placing servers, compute, hardware across multiple geographic locations, we need to ensure that we understand the data sovereignty laws in that location. We also want to understand what kind of availability we have in that location and any sort of restrictions that we may have, like compute restrictions or storage restrictions. Okay, let's talk about scaling now. So scaling is really, again, just an umbrella term that describes how we make our systems more robust for an influx of user connections or capacity. So we have two types we're going to talk about here in the SecurityX exam, vertical versus horizontal. So vertical scaling involves adding more resources to a single device. So we have, let's say, a server that we bought, let's say a capital expense. So we bought a server for on-prem, and we bought it to grow with our company. That's vertical scaling, where maybe we have, 10 petabytes worth of storage. We have a bunch of GPU, a bunch of CPU, 2,480 gigs of RAM, but we don't use it all. So we don't provision all that. It's sitting there in our hardware, but we're not using all that. We're not provisioning all that. And then the moment we need those extra compute or storage resources, we can then provision it. That's vertical scaling. Horizontal scaling is resource pooling. Horizontal scaling involves adding more systems instead of increasing the size of one. So it's multiple systems clustering or pooling together. This is kind of the more modern way to do it, especially when working in the cloud. If we deploy a single container to function as some sort of web application for our users, and then we get more users, more employees, whatever the case may be, more connections, we start to cluster other containers and then start to orchestrate that scaling with automation tools and technologies to always be able to scale dynamically to our influx of user connections, using things like Kubernetes and, of course, like infrastructure as code technologies like Terraform. Okay, persistence versus non-persistence. Persistence refers to whether a system retains data or state locally across restarts. Persistent systems store data on local or attached storage, while non-persistent systems are designed to be disposable and stateless. Non-persistent systems improve availability by allowing failed components to quickly be replaced. If a system fails, a new instance can be created and added to service with minimal effort. Okay, let's go ahead and do our quiz. So now we've finally moved on to domain 2, guys. So let's go ahead and do domain 2. Okay, question 1. An organization deploys its applications across multiple geographic regions to improve resilience. After a regional outage, users report seeing outdated or conflicting data depending on which region serves their request. What is the most likely cause of this issue? So we put applications across multiple geographic regions, but after a regional outage, we still have conflicting data. So I'm going to go with, it's not going to be improper load balancing. It could be an improper configuration though, but not just purely load balancing. It wouldn't just be a pure load balancing problem. Vertical scaling has nothing to do with it. Network segmentation wouldn't hurt or make this better. So I'm going to go with C. Inconsistent data replication between regions. Okay, question 2. An organization runs a customer-facing application that must remain available during server failures and traffic spikes. The application uses multiple identical backend servers. However, users sometimes experience inconsistent behavior depending on which server handles their request. Which design issue is most likely causing this problem? Okay, customer-facing application during failures and traffic spikes. It's kind of like the same question as last time. If there's inconsistent behavior depending on which server handles a request, that means the backend systems are just inconsistent. Our backend logic isn't in the same state across all those front-end facing applications. Okay, question 3. During a security architecture review, an organization identifies that attackers could gain access to internal systems if a single perimeter control is bypassed. The security team wants to limit lateral movement within the network while maintaining operational stability. Which design approach best addresses this concern? So attackers could gain access to internal systems if a single perimeter control is bypassed. So perimeter control is going to be like a firewall. They want to limit lateral movement, so we want to segment. So I'm going to go with D here. Implement internal firewalls for network segmentation. So we can just have like multiple firewalls, right? Or logically have multiple firewall instances in one hardware, or like even route instances. Okay, moving on. Question 4. An organization is designing a highly available network for a critical application where downtime cannot be tolerated. The security team wants visibility into network attacks, but must ensure that security monitoring tools do not introduce new points of failure. Which solution best meets this requirement? Okay, so we don't want downtime, but we want more visibility, but we don't want any points of failure. So we don't want anything intrusive, essentially is what we're saying, anything that can be exploited or potentially block our traffic. So I'm going to get rid of IPS. It doesn't say web application, so I'm not going to be a WAF. And we're just worried about visibility. A forward proxy could help us do that as well. But an IDS is like purpose-built for that, right? So I'm going to go with B. Yep, deploy and introduce a detection system using a network tap. Okay, moving on. Question 5. A company exposes several APIs to third-party developers and has experienced performance degradation due to excessive requests and abuse. So like we need some rate limiting on there. The security team wants to enforce authentication, limit request rates, and protect backend services without modifying each application individually. Okay, so yeah, they pretty much we need to make a gateway. We need to make a central place where all these API requests come in. So that's going to be C, API gateway. All right, last question for this quiz. A company wants to ensure that critical systems can be restored quickly after a ransomware attack, while also ensuring that restored data is accurate and trustworthy. Which design consideration most directly supports both availability and integrity? Critical systems can be restored quickly after a ransomware attack, and we need to make sure we have integrity on that data. Okay, so scaling has nothing to do with it. Load balancing has nothing to do with this restoration. Non-persistent would be the opposite. If it said persistent computer instances that are backed up, it could be D, but we're gonna go with A here. Well-tested backups with defined recovery objectives. All right, awesome guys, another 100%. So when did we get back? Like at 12:50 I started teaching, so been yapping 25 minutes. Let's just take another 5-minute break, guys. We'll just do 5, and then we'll move on to the rest of domain 2. All right, guys, let's go ahead and move on to domain 2.2. So domain 2.2.1, given a scenario, implement security in the early stages of the system's life cycle and throughout subsequent stages. So security requirements definition and software assurance we're going to be going over in this slide deck. So here's the exam objectives, and in red is what we're going to be going over. So functional security requirements. So functional security requirements describe specific security behaviors or capabilities that the system must perform. So examples of this is like requiring users to authenticate before gaining access, enforcing RBAC, encrypting sensitive data, logging security-related events, or just logging in general, right? So functional security requirements are critical because they can be directly implemented by developers, validated through testing, and used to define minimum acceptable security behavior. And I deal with this when we implement a new hardware. Like we're going through a life cycle right now for our edge routers. Even though my router is going to be able to do the base routing functionality, part of it is a SIA, it's like a security impact analysis, to ensure that the foundational security requirements that we already have in place isn't going to meet that same or do even better, because we have to meet something called an ATO, authority to operate. So this is something we do in the government as well, or any cybersecurity focused organizations do as well. So non-functional security requirements. Non-functional security requirements describe the qualities and constraints that determine how well the system protects itself rather than what specific action it performs. Examples include requirements stating that data must be encrypted using industry-approved algorithms, that the system must remain available during denial of service attempts, or that the system must comply with regulatory frameworks such as HIPAA or PCI DSS. So when I was kind of making this slide, I remember making it because it actually finally puts an exam objective, security versus usability, and that trade-off. It was kind of always like an unknown thing that you must teach this when going over the CIA triad, but it was never like clearly defined. So I'm glad it's going over this now. And what we're talking about is as much as you harden and secure and reduce the attack surface and put layers and layers of security over an environment or over technology or service, the less available it is. And what we really mean by that is not that, oh, you don't have network connectivity to it, the less usable it is. I don't know if some of you guys have been in a while, but when SoftNet U first became the standard strategic global enterprise that it is now, you know, back in like, I think 15, 16, 17 is when, I can't remember the exact year, even you got to the field, it was SoftNet U. It used to be like our own tactical domains. It used to be like taclan.mil or something like that, right? Where we used to make our own user accounts that would be just for that tactical network, okay? It was super easy, super usable, and we could quickly get services up for our users, for the AOB, right? But then once it went to like SoftNet U, it would take like 30 minutes to log in to a computer. And that was when we'd go to the field and like we'd bring out our own like tough books that the users would use instead of them just bringing their own laptops with them now, which is kind of like the standard now, right? People just bring their own computers so things are cached. But it was like, essentially Nipper was like unusable, man. Like you couldn't do shit on it. You could email, you could get some stuff off the share drive, but nowadays they made really long strides where I don't even care that I don't have commercial in my office anymore. I used to have commercial in there, I'd use it all the time, but now Nipper's fine. Like YouTube runs a little slow, yeah, some things like that, but it's very usable now. So that's just a real world example of that trade-off. The more hardened, the more locked down you make something, the less usable it is for your users. Okay, let's get into some application testing. So static application security testing. So static application security testing analyzes source code, bytecode, or binaries without executing the application. What we're saying here is that during a code review, if you're doing code reviews as a cybersecurity function, to make sure there's nothing vulnerable, no bad libraries, no plugins that could be vulnerable. SAS, or static application security testing, is just analyzing source code without it being in a runtime environment. So it's just looking at the code repo, combing through it, and seeing if there's anything just from the code that you can tell may be a vulnerability. Dynamic is doing the same thing, but you're actually running that code now in a runtime environment. So now you're actually doing tests against the actual application. You're not just looking at the application source code, you're actually running the application, and you're you have tools to interact with that application in a runtime environment. Now I'm saying runtime because it doesn't mean you deploy that to production and then you try to crash it. It means you put it in some sort of staging, testing, or runtime environment, whatever that may be, right? And then you test against it. And what you're looking for is misconfigurations, common attacks, right? Common vulnerabilities that have nothing to do with like software operating system versions, not like active campaigns. We're just looking at misconfigurations, validation errors. Can we do an easy cross-site scripting attack? Things like that. Okay, interactive. So interactive application security testing combines elements of both static and dynamic. Interactive application security testing tools operate inside the application runtime and observe application behavior as real requests are processed. So kind of a combination of both, looking at how the code functions, and you also see the front-end results, back-end results, database results, all through one single tool here. Okay, runtime application self-protection, or RASP. So runtime application self-protection embeds security controls directly into the application runtime. Rather than identifying vulnerabilities, RASP actively blocks exploitation attempts as they occur. And then we have vulnerability analysis and SCA. So vulnerability analysis, we've talked about this a lot with vulnerability management, is essentially we have a vulnerability scanning system in place. We get a sheet of paper, we get an output from our vulnerability scanner that says, hey, these systems or these operating systems have these many vulnerabilities, 10 lows, 5 mediums, 2 highs. And then we say, okay, well, what are we going to deal with first? More than likely, we're going to deal with those highs first and then work our way down to the mediums and the lows. So modern applications rely heavily on third-party libraries and open source components. Software composition analysis identifies these dependencies and evaluates them for known vulnerabilities, outdated versions, and licensing risk. SCA is critical because many real-world breaches originate from vulnerable third-party components rather than custom code. And the last thing we're going to talk about here is an SBOM and formal methods. So this is kind of like getting into like procurement and understanding when we get software and dealing with vendors. So a software bill of materials is a formal inventory of all components used within a software product. I'm going to leave it at that. It helps us with our asset inventory. We can build it ourselves, or we request one usually from the vendor as well. Formal methods apply mathematical and logical techniques to verify software correctness and security properties. Rather than testing for defects, formal methods attempt to prove that certain classes of errors cannot occur. To be honest, guys, maybe just I haven't been in the industry long enough. I've never heard of this until I made this slide. I have no idea what they're talking about when it comes to formal methods. If you see it on the test, just try to memorize this because this is like kind of book definition that I grabbed, right? When I don't know something, I kind of just go straight to the book and look up definitions. But yeah, I'm assuming what this is saying, kind of like we're a GPS, we need atomic timing. We need something that's accurate, not based off a protocol that thinks it's accurate. That's the best way I can kind of make it make sense in my head. Okay, let's do a quiz. Domain 2.2.1. Zoom in a little bit. All right, question 1. An organization wants to identify vulnerabilities that only appear when an application is running, such as authentication logic flaws and session management issues. The security team also wants to test the application from an external attacker's perspective without access to the source code. Which software assurance technique best meets these requirements? So we need an application in a runtime environment, and we don't want access to the source code. So that's dynamic. That's not going to be B or D, because we'll need access to the source code. And A literally is looking at source code. So we're going to go with C here, dynamic application security testing. Interactive application security testing also wouldn't work, right? Because that's an agent, that's a tool plugin that actually gets access to source code. So this question is exactly describing dynamic analysis here. Okay, question 2. During the early planning phase of a new application, a security architect states that the system must enforce role-based access control, require multi-factor authentication for administrative users, and log all authentication attempts. Which type of security requirements do these statements represent? So this is our basic security functions that can happen regardless of what compliance, what governance you have, or what tools, technologies. It's going to be B, functional security requirements. And the last question here for this domain 2.2.1 quiz. A development team embeds a security component directly into an application's runtime environment to automatically block malicious input, prevent unauthorized code execution, and terminate suspicious sessions in real time. Which software assurance approach is being used? So we need something directly in the application's runtime environment to block malicious input. So this actually is an active process that's in a production code. So that is going to be B here. Runtime application self-protection. And there's our explanation. Okay, sweet guys. I feel like I'm going a little faster with these slides because we got a lot to get through. Whoa, what happened? So let's go ahead and finish up domain 2.2 now. Domain 2.2.2, given a scenario, implement security in the early stages of the system's lifecycle and throughout subsequent stages. And we're going to be going over CI/CD pipelines here in supply chain and EOL. So here's our exam objectives in this slide, and in red is what we're going to go over. So CI/CD pipeline, continuous integration, continuous deployment, or continuous development, sometimes you hear it. What is it? This is just a method to which we can quickly create something called MVPs, minimum viable products, into our coding and development pipelines. CI/CD pipelines give us the tools, the technologies, and the methodologies, and the release cycles, and the operations to actually accomplish that. A continuous improvement cycle into our applications. So that's what the CI/CD pipeline is. And now, from a cybersecurity perspective, how can we input security controls into this CI/CD pipeline to ensure that we are doing our due diligence and being proactive in securing our applications that are in this pipeline? So we're going to go over some things. So coding standards. So one thing we can have in our environment is coding standards. These are defined rules and conventions developers must follow, and it makes reading the code a lot easier for people within the organization to discover vulnerabilities. Then we have something called linting tools. Linting tools are automatically analyze source code to detect violations of coding standards. So essentially, we create the coding standard, and then we make a linting tool that'll tell us, or it'll be like a little red arrow there that says, hey, no, you need hit the tab key instead of space 3 times for this sort of like convention, okay? So by enforcing linting in the CI pipeline, insecure code is rejected early in the development process. Branch protection. So if you guys have ever, this is what I make my engineers do actually. Oh, I wish I could show you guys on Nipper. Anyways, so we host all of our code in GitLab. And then that's for all of our aircraft kits and for my my regional ground entry points, all my data centers, right? So or make something better, they can create a new branch. And then they can submit a pull request or a merge request for that new branch to go into the main branch, okay? So that is something that is very common. Like if you go work at any industry, civilian side, you use GitHub or you use GitLab or you use some sort of Git source control management for all your code, and there's gonna be branch protection. And usually only like the most senior person will have rights to that main branch to make changes into it, because that main branch is literally your production code, right? All right. Yeah, every time I teach like Soph a lot, like white Soph, so like group, and you guys always complain about that Mevo shit. I've never seen it myself, but I don't know. So I was like, let me ask this government guy why they did it. And he like rolled his eyes and was just like, well, I know everyone hates it, but it's because they don't understand their equipment, so we have to do it. I'm like, all right, bro, well, I was just curious. And now you guys are the first class I can actually tell you about a little bit behind the scenes. All right, continuous improvement. So security threats constantly evolve, new vulnerabilities, attack techniques, and defensive strategies emerge over time. Continuous improvement means that security controls within the CI/CD pipeline are not static, but are regularly reviewed and enhanced. All we're saying here is that you got to embed yourself into that agile methodology and framework of continuous improvement and ensure that you're doing your due diligence as a cybersecurity professional to ensure that the code is protected and they're using good coding standards and best practices, and that you're looking at the third-party libraries that they may be integrating. Okay, now let's go over some different types of testing. Y'all ready? Unit, integration, and regression testing. So let's go over these. Unit testing. This focuses on individual functions or components within an application. And from a security standpoint, unit tests validate that security critical logic behaves as expected. Integration testing. This examines how different components interact with each other. Many security vulnerabilities emerge at integration points, such as when data passes between services, APIs, or systems. So this is kind of like, here's our unit testing here. Now we're putting that piece of that puzzle into a larger pie here, the bigger puzzle, and seeing how it fits. And then regression testing, and when we take that puzzle piece away, did we break something? Or did that old vulnerability come back up? Okay, canary and automation testing. Not that they're that they need to be combined, but we're gonna go over canary testing and automation testing. So what is canary testing? It's actually something that happens to you guys, like, okay, if you use YouTube, if you use TikTok, Instagram, all the big social media apps, they all do this. I call it A/B testing. The co-founder of Trevor Technologies was an L6 meta engineer. He also calls it A/B testing. I don't know why they decided to use canary here in CompTIA. I feel like whoever makes their exams is some like old school professor that, anyways, that is not in industry, but just be writing for them. But all it is, guys, is we have our standard version of our web application that you're accessing, and we want a new feature that marketing thinks that will be great and get more eyes and get more whatever, more money, more clicks, whatever the case may be. So we make this new version of our web application. It could just be a color scheme though. It could be anything, right? And we say, hey, marketing, well, we want to test this against our user set first. One, to make sure it's still functional with our users, but to see if it actually drives the metrics you're looking for. So 96% of our users will get our standard version. I put old there, but whatever, right? Of the standard, and 4% of our users will get the new. And then we'll try to get metrics on those 4% of those users. I run a YouTube channel with I'm almost at 5,000 subscribers too. But they gave me this ability too with my thumbnails. So I can actually show you guys real world canary testing. Hold on. So let's see here. Let's say I go to upload a video. I select files. Let me just go to a quick movie real quick. So you see this A/B testing here? So I can test different titles and I can test different thumbnails. So that's canary testing. Why they called it that for the CompTIA test, I really don't know, right? Really not sure. Okay, but automation. So now automation is essential for maintaining security at scale. Automated security tests run consistently and do not suffer from fatigue or oversight. Every code change is evaluated against the same security criteria. Okay, now let's go over supply chain risk. I've talked about supply chain so much, so I'm not going to spend too much time on this. So software supply chain risks. Modern applications rely heavily on third-party libraries, frameworks, and open source components. These dependencies accelerate development. They also introduce significant risk. So what we're saying here is that when you're integrating plugins, third-party libraries that you didn't create yourself, that are not well vetted, you could introduce risk. Hardware supply chain risk. Same thing. Depending on where you're getting your hardware from, there could potentially be a vulnerability on there. There's a reason why the DoD, we never buy Lenovo. Even though I love Lenovo, they actually make great laptops, but where do they come from? China, right? So that's a hardware supply chain risk that we're not going to accept. Okay, hardware assurance. So hardware supply chains introduce different but equally serious risks, including counterfeit components, tampered firmware, and embedded backdoors. So how do we make sure that our hardware, how do we get insurance from the vendor that it has not been tampered with? Well, we can go into like a contractual thing with them. We can get with our VARs, our value-added resellers, and say, hey, make sure that the hardware you're supplying to me, I'm a managed service provider, that it is from the vendor itself, and there should be some sort of like SLA involved in there. But really, you can't, right? If the OEM, the original equipment manufacturer's hardware gets tampered with in the supply chain logistics that you don't even see, that they might not even see as the OEM provider, you know, their chipsets, whatever, you really can't get that insurance other than something in paper. Okay, end of life considerations. I already talked about this. Every system goes end of life. So end of life does not necessarily mean end of support. End of life means that it's no longer going to be sold on the shelves. What you need to make sure is that whatever vendor you're going with, that those terms are clearly defined. Because they're supposed to be different, like end of sale, end of support is kind of what I like. End of sale, end of support makes sense to me. End of sale could be 2025, but I can still keep that hardware in my environment till 2029 when the end of support date comes. End of life sometimes get wrapped up all into one. Depending on how big the vendor is, they just may say end of life, and they just may, that to them means both. We're not selling it and we're not supporting it. So you just gotta kind of define those dates with the assets that you have in your inventory or in your enterprise. Okay, let's do this quiz now. Alrighty. You guys want to see what's in store for you if you go work at a